right? So, remarks. Backward Euler right, which is alpha equals 1, damps out, well, I don't like the term damps, I'm going to say dissipates. Dissipates high order modes. Okay, and this is what we call numerical dissipation. Okay, and because, as I observed, this has the same high order behavior as the exact equation, it is often preferred. Okay, numerical dissipation, right? And let me also say here it is similar to time exact equation. Right. The second note here is that there really isn't much to say about forward Euler, by the way. It should come as no surprise to us as that the amplification factor for forward Euler tends to minus infinity as lambda h delta t gets large. We've already seen some evidence of it. And in what way have we seen evidence of it? We've seen it in the fact that if delta t gets too large, we know that the forward Euler method is no longer stable, right? And that is also reflected in the amplification factor going to getting unbounded, in this case minus infinity, as delta t gets too large, right? Remember, lambda h delta t can get large if either lambda h or delta t get large. If you have a large time step, we know that there is a tendency for forward Euler to blow up, so to speak, right? And we see that in the amplification factor tending to minus infinity. Okay, so let me state that though. Forward Euler which is alpha equals 0, has unbounded lambda, has unbounded A. Okay, all of this, by the way, is in the context of high order modes, right? So I should say up here, this is all for high order modes. Okay, so everything I'm writing here applies to high order modes. Okay, right? So this should come as no surprise to us because we know that forward Euler has this tendency to sort of lose it. Okay. Remark 3 is that the surprising thing is that the midpoint rule or it may be a surprise, right? The midpoint rule, which is alpha equals 1/2, right, has, as we've seen, A tending to minus 1. Okay, what does this mean? What this means is that dn plus 1 for the high order modes, right? If this is a high order mode I'm writing out, right? Okay, if dn plus 1 is the modal coefficient of a high order mode, what we're seeing is that dn plus 1 is equal to minus dn. This leads to oscillatory behavior in the high order modes. And it's not uncommon to see solutions for from the midpoint rule, which with respect to time, right, if we're plotting certain modes with respect to time, what we will see is that if this is t1, t2, t3, and so on, right? What we may very well see is that you get get essentially oscillatory behavior. Okay. Something that's done is to simply form a time average. Okay. Right. If you take a time average, you basically damp out, well, you don't truly damp out, but you eliminate the effect of these oscillations in your post-processed solution. Right. Time averaged the solution. Okay, to get around this. All right. This is important to know about the behavior of these methods in the high frequency limit, right, for high order modes. Okay. So we've looked at stability, we've understood the behavior of high order modes. What we are going to do next is essentially prepare ourselves for talking about convergence. All right. And the way we do that is by first looking at the notion of consistency. Okay. So we look now at the idea of consistency. All right. In order to get to consistency, let's go back to our time discretized equation. Okay. And that equation, as you may recall, is the following. It is dn plus 1 times 1 plus alpha. Oh, no, let me back up a little here. Let me write it, in fact, in the following manner. Let me write it all the way back as dn plus 1 minus dn over delta t plus lambda h dn plus alpha equals. Now, up to a few seconds ago, we were looking at the homogeneous problem, right, which we got to by turning off the high order modes. Sorry, by turning off the forcing. We're now bringing back the forcing, okay? And I'm going to write this as f at n plus alpha on the right-hand side, okay? If you wonder what fn plus alpha is, fn plus alpha, right, for this particular mode is got by looking at f sub n plus alpha, the whole vector, right, and essentially, right, dotting it with whichever mode we're looking at. Okay, if we were looking at mode L, we would dot it with the Lth mode. Okay, but since we've agreed that we're going to drop the explicit mention of the modal number, right, we will just write it as fn plus alpha here. Okay, all right. Now let's multiply through by delta t and see what we get. We get dn plus 1 minus dn plus lambda h delta t. I'm going to expand out dn plus alpha as alpha dn plus 1 plus 1 minus alpha dn equals delta t f n plus alpha. All right. Working with this a little more, what we get is dn plus 1 times 1 plus alpha delta t lambda h minus 1 minus alpha delta t lambda h dn minus delta t fn plus alpha equals 0. As a final step, I'm going to divide through by 1 plus alpha delta t lambda h to give me dn plus 1 minus, now when I divide this quantity by this, I get back my amplification factor. So I'm going to jump a step and simply write that as a dn minus delta t divided by 1 plus alpha delta t lambda h fn plus alpha equals 0. Okay? Right? And I'm going to take the final step of calling this quantity here L at n plus 1. Okay? Or I think I call it doesn't really matter. Let me just call it L at n. Okay. All right. So this is how I want to write out my time discrete modal equation, right, including the forcing. Now, the notion of consistency is the following. What would happen if you were to take the time exact modal equation and plug it in here? Okay, so let me now write that as d at tn plus 1 is the time exact mode corresponding to lambda h. Okay? The particular value of lambda h gives us a certain mode, and that's it. Okay? Now the question we ask is what would happen if we were to take our time exact modal solution and plug it back in here. All right? So what we are saying is that if we do that, we'd get d at tn plus 1 minus a d at tn, right? This is also the time exact modal value at time tn minus minus ln. Okay, because the last term ln does not depend upon the modal values. Okay, now this equation is equal to 0, right? The left hand side on this equation is equal to 0. My question is, if we were to now plug in our exact solution here, right, as I've done, will what I've written here on the left hand side be equal to 0 or not? In general, it's not equal to 0. Okay? In general, however, one can write it out as delta t times some quantity tau. Okay? Tau, which in general depends upon the time. Okay? Right? The reason we're writing it out as delta t times tau is that because we recognize that having started from this form of the equation, we've actually multiplied the ODE through by delta t. So we expect that whatever the right-hand side is, it already has a factor of delta t sitting in there, right? So we choose to write it in this fashion. Okay? Now, this is the general form that we would get for the exact equation, right? It turns out that we can now make the following identification. Okay? What we say is that, sorry. Actually, let me back up to the previous slide. Let me just say one more thing here. If we can show that our exact solution satisfies an equation of this type, okay, we have what we call a consistent method. well, it's no, let me back up a little more. It's not quite a consistent method. This is a consistency condition. Okay, this is a consistency condition where we have a consistent method if we can show further that tau, which I've written as depending upon the actual time, if we can show that tau is lesser than or equal to some constant c times delta t to some power k, okay, where k is greater than 0. Okay? If we can show this, then we have a consistent method. Here's why. If we can show that this holds, one can say that as in the limit as delta t tends to 0, right, what we will find is that d at tn plus 1 minus a d at tn minus ln, which is equal to delta t c delta t to the power k, right? This thing also tends to 0, right? This entire thing also tends to 0, okay? Right? If k is greater than 0, right? And therefore, what this suggests is that, yes, the equation we are working with, the finite difference equation we are working with in time, is one that when we plug in the exact solution, though it does not immediately satisfy the exact solution, at least it does satisfy it in the limit of vanishing time steps. Okay, so in the limit delta t tends to 0, the time discrete equation admits the exact solution, right? And which I'm sure you will agree is a useful property for a method, right? For a numerical method. Okay. I should mention, of course, that in that result, t of tau n is lesser than or equal to c delta t to the power k. C is a constant, and k is what we call, k is the order of accuracy. Okay, and it turns out that k equals 2 if alpha equals half, right? The midpoint rule. And it's equal to 1 otherwise. Okay? All right. So the midpoint rule, as you may expect, because it does look at it does apply the algorithm between n and n plus 1, gives you higher accuracy than any of the other methods, right? Backward Euler and forward Euler are down here. And any other method also has order of accuracy 1. Okay? Only the midpoint rule is second order accurate. Okay, this would be a great place to end this segment.